Now we are interested to find the value of beta in this equipartition theorem, in equipartition formula that is derived by Boltzmann. Now, according to him, that each particle should have this much of energy, that is the energy per particle. So each particle should have this much, this by 2, so this much of energy, and this multiplied by its degree of freedom. So its degree of freedom. So according to classical physics, he said that every moving particle is associated with this much of energy, kBT, where kB is Boltzmann constant into temperature in Kelvin by 2. So this into the degree of freedom of the particle. So degree of freedom means the direction in which the motion of the particle is possible. So it is justified up to certain extent. For monoatomic gases, we have seen that this is absolutely correct. For diatomic gases, up to some extent we can say it is correct, not at very high temperature. But when the temperature is increased or the structure of the molecule is different, sort of linear or non-linear structure, then this phenomena is not followed. So whatever, say for general purpose, if we say try monoatomic gas. So for monoatomic gas, if we take this linear degree of freedom, and that is equal to 3, that is one is in x-axis, in y-axis and in z-axis. So basically we are, whatever we are calculating here, so this is for monoatomic gas, that means it has only linear motions. We are not considering any vibrational motion. We have considered it that particle is like wave, but we have not considered that particle has spin and that particle can also rotate. So these things we have excluded. So according to that, so this degree of freedom should be 3. So energy by total number of particles should be equal to this much, 3 kBT by 2, and total energy of the particle is multiplied by n, so 3n kBT by 2. So this is according to the classical physics, this is the result that Boltzmann obtained. But now we are approaching in a different way. So now we are interested to find the energy of the particle, the total energy of the particle. So the total energy of the particle can also be given as this is the summation of energy epsilon and the number of particles having that energy and the summation of all those. So as we have done this EI into Ni. In our previous classes we have done this, that EI into Ni, and summation of all these is the total energy of the particle, and that is constant for a particular volume. So here also we want to do this thing, but it is not discrete. Now we have taken the wave formation, that the wave format of the particle. So for this number is related with this. So this is number of particle having energy epsilon can be given as, that is the energy space into F. So this F of epsilon, this is called that this function. So this function is known as that is called the occupancy function. So this is actually the energy space into occupancy function. So these two, the multiplication of these two is actually the number of particles having energy epsilon, and this multiplied by the energy of a single particle. So this total thing should give the energy of the total system, total energy of the n number of particles. So if we use this, and this is not discrete particles, this is all the particles moving like wave. So for this we require integration here, so not discrete summation. So if we do integration from 0 to infinity in positive side, then we should get the same result. So that is to be checked. So we can write that energy of the particle is actually integration 0 to infinity, and this energy of a single particle, and this thing, that is V by, that is the energy space, V by 2 pi square h hat cube into root under 2m cube and root under epsilon del epsilon. So this is this value, and this equal to e to the power minus alpha plus beta epsilon. So this is the occupancy function. So if we integrate this total thing, then according to that Boltzmann concept, so that value should be 3 by 2 n kVt. Now that is to be checked here. So what we do, so let us take the constants outside. So here the constants are, so these are the constants. I am writing E from here because the constants are very large here. So the constants are, this thing is totally constant, up to this is constant, e to the power minus alpha, so this is also a constant. So we are taking this outside, so this will be v by 2 pi square h hat cube into root under 2m cube into e to the power minus alpha. So this is taken out, and integration of 0 to infinity of this thing, root under epsilon, and there is another epsilon here, so this can be written as epsilon to the power 3 by 2, and this is e to the power minus beta epsilon del epsilon. So we have to integrate this part. So integration is not large, but this constant part is very large. Now e to the power minus alpha, we have already derived the value of e to the power minus alpha in our previous class. So those who have not seen this class, so please go and see that class where I have derived the value of e to the power minus alpha. So however, if I put the value of e to the power minus alpha, then I think it will be a little bit smaller. So if I put this v by 2 pi square h hat cube into e to the power minus alpha is this thing, so this is 4 pi number of particles by volume, this into 2 pi square h hat cube, and that is beta, so I am writing cube inside such that the calculation becomes easy. So this will be 8 pi cube m cube, so root of this. So this is actually this thing. So okay, so this is the value of these constants, and the integration from 0 to positive infinity epsilon to the power 3 by 2 e to the power minus beta epsilon del epsilon. Now let us see what things are actually cancelled. So this thing and this thing is cancelled. This volume, this parameter is also cancelled. So we are getting 4 pi n. So take this out, 4 pi n. And this is also under the root, and this is also under the root. So we will make this total under the root. So it will be into under root 2m cube beta cube by 8 pi cube n cube, and this is integration 0 to infinity epsilon whole to the power 3 by 2 e to the power minus beta epsilon del epsilon. Okay, so here also you can see that this m cube and m cube is cancelled, and this is 2, this will be 4, and the root of 4 is 2, so this 2 will come outside, so this will be 2 pi n, and this will be only beta by pi, so this will be beta by pi, so this is beta cube by pi cube. Okay, so this thing, so we can also cut it, so such that this will be 2n beta cube. So let us do this. So this will be 4, this is 2, so 2 is cancelled, so 2n, and here it is coming that pi, you know, this is under, okay, sorry, so this cannot be done now. So we have to do this 2 pi n, and this is beta by pi whole to the power 3 by 2, let it be in this way, okay, and the integration of this 0 to infinity, and this is epsilon whole to the power 3 by 2 and e to the power minus beta epsilon del epsilon. So this is our thing. So now I am writing this over it. Okay. So that we are finding actually the total energy of n number of particles. So we have come to a big calculation, but the calculation actually becomes smaller when we put the value of e to the power minus alpha, whatever. So the value of E is equal to 2 pi n, and that is beta by pi whole to the power 3 by 2 into say I, where this I is equal to integration 0 to infinity, and this is epsilon to the power 3 by 2, and this is e to the power minus beta epsilon del epsilon. Okay, so just we have to find out the integration of this thing, then we can calculate what is the total energy. So to calculate this, let us let root epsilon equal to x, such that differentiating 1 by 2 root epsilon del epsilon equal to del x. So we are getting del epsilon is equal to 2 root epsilon del x, and root epsilon is again x, so this can be written as del epsilon is equal to 2x del x. Okay, so this del epsilon can be changed as 2x dx, and e to the power 3 by 2, so this can be written as, this is x cube. Okay, so the integration becomes, and this is going from 0, the limit is 0 to infinity, so as root under epsilon is x, so the limit is not changing, so this will be from 0 to infinity, and this will be root epsilon cube, so this will be x cube, and e to the power minus beta x square, and this will be 2x dx. Okay, so this is our integration. So first we require, so take this one as the second function and this one as the first function. So integrating by parts, we will get x cube and integration of this. So 2x dx means actually del of x square. So here also x square is present, e to the power minus beta x square by minus beta, and minus of integration of this thing, so this same thing, beta x square by minus beta into differentiation of x cube, that is 3x square del x. So this thing, and we are integrating from 0 to infinity. Now notice that, like our previous lesson, so if we integrate this from 0 to infinity, so if we put infinity here, so e to the power minus infinity will give it 0, e to the power minus infinity is 0 basically, tends to 0, and if we put 0, so this will be 0, so this total thing will be 0. So only remaining thing is here, this thing, so it is, let it take outside, so this will be 1 by beta, and integration, so here only 3 is there, so this will be 3 by beta, and integration 0 to infinity e to the power minus beta x square and x square del x. Okay, so now this is the integration. Now whatever we have to do, that we have to take one x outside, so let us do like this, 3 by beta, and consider it like this, that is x and 1 is 2x. Okay, e to the power minus beta x square into 2x del x. Okay, so we have to give 1 2 here. So this e to the power minus beta x square 2x, this will be a second function and this will be the first function. So again we can integrate by parts. So we have to make it small at first. Okay, I'm erasing just this part. Okay, so from here, if we integrate this, so by parts again, so there 3 by 2 beta is already present, and we have x, and integration of this part will be e to the power minus beta x square by minus beta, because 2x is here, and minus integration e to the power minus beta x square by minus beta, and that differentiation of x is 1, and del x. So this from 0 to infinity. So again, if we put infinity and 0, so this part will be 0, the remaining part will be this. So now one beta will come here and this will be multiplied with this thing. So this will be 3 by 2 beta square and integration 0 to infinity e to the power minus beta x square del x. So the thing is coming here. Now, who have seen my previous class, they have seen that in case of this sort of integration, what we have to do, we have to make it Jacobian, otherwise it is not possible to solve this. So we do it, one I is like that and another I is in the format of 3 by. So the constants will remain same, just we will change the variable. So we will write it e to the power minus beta y square and del y, and then we will multiply these two. So this I multiplied by this I, so this will be giving I square, and this will be 9 by 4 beta to the power 4 integration 0 to infinity, and again integration 0 to infinity, and this will be e to the power minus beta taken common, so this will be x square plus y square, and this will be del x del y. So if we write x equal to r cos theta and y equal to r sin theta. Okay, so x square plus y square gives you r square. So this is number 1. And also, as theta is very small, theta tends to 0. So you get x is nearly equal to your, so this will be equal to r, because cos theta, if theta tends to 0, then x tends to r, and here also y tends to, it is not r, it will be r theta. So del x will be equal to del r, and del y will be equal to r del theta. So by this approximation, and also y can be taken as r tan theta. So if we take y is equal to r tan theta, because theta is very small, that's why you can take this sort of change can be done. So if we take y is equal to r tan theta, so theta will be equal to tan inverse y by r. So y tends to 0 to infinity, so for 0 this will be, theta will be 0, and for infinity, so theta will be pi by 2. So transforming this into Jacobian, you will get this result. So this will be equal to 9 by 4 beta to the power 4. So this will be theta equal to 0 to pi by 2, and this is the value of r, 0 to infinity. So e to the power minus beta r square, and this will be your r dr d theta. Sorry, del r del theta. Okay. So this will be the thing. Now at first we will integrate this part, then we will integrate this part. So let us see what is the result here. So we are calculating I square. Okay. So in calculation of I square, we have seen this I square is 9 by 4 beta to the power 4, and integration of theta is equal to 0 to pi by 2. So take del theta here and separately integrate r equal to 0 to infinity, and this is e to the power minus beta r square, and this is r del r. So one integration is this, another is this. So this can be done fairly easily because this is just theta. So it will be pi by 2. So this will be 9 pi by 8 beta to the power 4. Okay, and this will be integration of 0 to infinity. Give a half here, so that you can take e to the power minus beta r square, and this is 2r del r. So now this can be integrated very easily. So this will be 9 pi by 16 beta to the power 4, and the integration of this part will be e to the power minus beta r square y minus beta from 0 to infinity. Okay, so take this beta outside, so constant outside, so make it 9 pi by 16 beta to the power 5, along with the minus sign will come. Okay, and here e to the power minus beta r square from 0 to infinity. Now once we put it infinity, so you get e to the power minus infinity, which is basically 0, and e to the power 0, that will give you 1. So this thing will be okay, so this is coming minus 9 pi by 16 beta to the power 5, and if we put here, so this will be 0 minus of if we put 0, then it will get 1, it will give you 1, so minus 1. So this minus is cancelled, this is positive, so this is giving this by 16 beta to the power 5. Okay, so the value of I, only integration, will be root of this, so this, and root under pi by beta to the power 5. So this is the value of the integral of this part. So this integration actually results in this value. So 3 by 4 and root under pi by beta to the power 5. So this is the value of this integral. Now if we multiply this constant with this integral, the value of this integral, then let us see what we get. So that will be the total energy of n number of particles. So the energy of n number of particles will be 2 pi n, and this will be, let us write this in this format, that this is beta cube, as because there is square root, so write it beta cube by pi cube, so square root of this into integral, so this is 3 by 4, and this is also root under pi by beta to the power 5. So this will give 3 pi n by 2, and root under, this is beta cube pi by pi cube beta to the power 5. So this is giving pi square and also beta square. So square root of this will be pi beta. So this will be 3 pi n by 2 pi beta. Okay, so pi is cancelled, so this is giving 3n by 2 beta. So if we mix this, the energy that we have got from this calculation, and this energy should be equal to that the classical calculation of Boltzmann. So he said that the energy of n number of particles, so he said that energy of n number of particles, that we have got 3n by 2 beta, and he said that n number of particles should have this much of energy. So from this, if we cancel 3n, and here 2 and 2, so we get 1 by beta is equal to kBt, that gives beta is equal to 1 by kBt. So yes, the value of beta is correct. The value of beta is correct. The value of beta is correct. Okay. So the value of beta is correct, but if we take degree of freedom into beta, a degree of freedom into your kBt, that may not be correct in all cases. And that is the case, that case you will find in black body radiation. And there are many other cases where just you cannot take the degree of motion and degree of freedom into kBt. So kBt is not actually a sort of unified energy quanta that can be added. So for that we have to come to Planck's derivation. So Planck said that energy comes in quanta, but that quanta is not necessarily kBt. So that quanta is not necessarily kBt. But in case of gas molecules, how far gas molecules is concerned, we can say beta is equal to 1 by kBt. So that is the value of beta. Okay, in our next class we will discuss about the RMS, root mean square velocity, and that is the probable velocity of gas molecules. Okay, thanks for watching.